All right, thanks for having me, and thanks everyone in the audience for tuning in to this talk. So I wanted to take this opportunity and just talk about our recent paper that tries to connect the AGN-driven outflows and the formation of dusty cold gas filaments in cool core clusters. So when we talk about galaxy clusters, we know the intra-cluster space is filled with X-ray emitting hot plasma, and in particular, in cool core clusters, the central cooling time for this gas is less than 1 billion years. So that means the gas has enough time to cool and form cold gas, feed a central black hole, and in turn, the central black hole will release AGN feedback that counters the cooling of the cluster. One poster child, one sort of the model system that we have for studying this phenomena is the Perseus cluster. It has a central AGN of X-ray luminosity of about 10 to 43rd ergs per second. And the AGN feedback can be beautifully summarized by this composite image on the right. You can see in violet, there are X-ray cavities that are inflated with radioplasma. So it suggests that in the past, it was inflated or driven by relativistic jets. At the same time, you can see in the optical range, there are these filamentary red excess, and these are H-alpha emission that's usually associated with 10 to the 4th Kelvin gas. So to study the effect of AGN feedback for my PhD thesis, I developed these simulations, tried to study the evolution of galaxy clusters under the influence of AGN feedback. And for here, I'm showing a pair of image comparisons between one of the snapshots in the simulation with the X-ray observation of the Perseus cluster. We can see that the AGN feedback can generate multiple cavities and ripples in the intra-cluster medium. And we believe that these waves can heat intra-cluster medium through processes such as weak shocks, sound waves, and more recently proposed by Tarazov's group, internal gravity waves. And at the same time, if we look at the properties of the cold gas, we've also shown in our paper that the AGN luminosity is positively correlated with the filament mass, the spatial extent of the filaments, but not so much with the velocity dispersion of the filaments. We've shown in our paper that only when the sightline is parallel to the jet X do you get a very weak correlation between the two quantities. The thermal H-alpha emission from the simulations is around 10 to the 42nd ergs per second, which is very similar to what we observe in the centers of cool core clusters around these filaments. So for this paper, which is the focus of tonight's talk, we wanted to answer the question about the formation of these filaments. Particularly, we want to ask 3 questions. First, where is the gas supply? Where is the gas coming from? The second is, how do these cold filaments coexist with the hot X-ray plasma? And the third one is just because we have seam dust in these filaments, how can we preserve the dust content inside the filaments? So actually, before I go to the simulation results, I wanted to show you this sort of rotisserie view of the filaments in our simulation and try to introduce the color scheme we'll be using later. So the black here is the neutral hydrogen column density, which is representative of the cold gas with temperature below 10 to 4 Kelvin. The orange here is the ionized hydrogen column density, which is representative of the warm gas we'll be introducing later. So let's begin this video, and just wanted to pay special attention to the left side of the left panel. You'll see over time, over a few billion years, you'll see the orange turns into gray, and then the filament kind of forms right here. I'll start this video again. At the same time, we'll also inject a tracer fluid from the center of the cluster just to be sure that the filaments do come from the central AGN outflows. So we now have a video evidence, sort of evidence to show that the filaments might have come from the AGN-driven outflows. To understand this phenomena, we divided the AGN outflows into 3 temperature bins. The first one is the hot component, with temperature larger than 10 to the 7th Kelvin. And the cooling time for such outflows are usually larger than 10 million years, so it's unlikely to cool within a short time scale to form the cold filaments. Instead, the warm component, which is sort of sandwiched between the hot and cold component, has cooling time less than 10 million years. So it's a very likely candidate for the formation of the filaments. By looking at this plot of outflow rates with different temperature components, we can see there's a spatial stratification of different components. For the inner 2 kiloparsecs, it's dominated by the hot component, and there's no cold gas outflows there. Beyond a few kiloparsecs, you can see the warm component slowly rises and eventually turns into cold gas dominated. So we think the process that helps explain this spatial stratification is the ram pressure from the intra-cluster medium. So to help illustrate this argument, we performed a simple analytic test. So here we're launching 3 different gas clumps with different initial temperature, and they're launched at 3,000 kilometers per second from the center of the cluster. Here we're looking at the radial, the temporal height evolution of these 3 clumps. You can see that the dilute hot and warm clumps are decelerated greatly before reaching their maximum heights, because the dilute gas usually have higher, larger cross sections, so you experience more ram pressure. On the other hand, the cold clump is actually not affected at all, so it kind of travels out to several hundred kiloparsecs, and that's usually never seen in real systems. Another interesting transition that happens in the middle is the warm branch. You can see that the gas cools within 10 million years, and then afterwards it kind of forms a cold component between 10 and 30 kiloparsecs. At the same time, we can look at the radial velocity evolution of these 3 branches. It would seem that we have 2 different scenarios of forming filaments from these outflows, but actually from observations we know there is actually an additional constraint on the velocity of these cold gas. For example, the each alpha line widths are usually less than 600 kilometers per second. And also from ALMA, we know that the molecular gas velocity is usually just a few hundred kilometers per second. So both of these tell us that the lower branch where cold gas forms from the warm outflows is more plausible. So we think the rate of cooling of the warm outflows and the ram pressure from the intra-cluster medium is the key in forming these filaments. The second question I typed earlier is, how do these cold filaments coexist with the hot X-ray gas? In other words, what constraints can we put on our model from X-ray oscillations? For example, here I'm showing a synthetic X-ray image of the hot gas. We can see through this combination of 3 snapshots that there's a cavity right here co-rising with the filaments. So this is also a phenomenon observed in real clusters where filaments are sometimes encasing or surrounding the X-ray cavities. If we look at the thermal properties of the hot gas, we can also, the quantity called cooling over freefall timescale ratio is often used to assess the thermal stability of the intra-cluster medium. Previously people thought that if the ratio falls below 10, then the gas will cool before it falls into the center, thus forming filaments in a precipitation manner. However, in observations, this is actually rarely seen. So values of below 10 is actually very uncommon in our observations, but with the exception of Phoenix, which is a very special system sort of in a turmoil of a cooling flow. But all the other systems, that we have observed have minimum cooling to free fall time scale ratio is usually above 20, right? So it kind of poses a challenge to the precipitation model of that we had before. But in our simulations, as you can see, so these orange dashed lines, dotted line actually, are the feedback regulated phases of the AGN evolution, and we can see it actually agrees pretty well with the actual observations of these cool core clusters. There's a recent push that also kind of supports our argument here, which is called the spoiler clusters. For example, A2029 is one of them. So in these clusters, even though they have profiles similar to other systems, because there are no outflows in these centers of cool core clusters, there are no filaments. So it kind of also supports the idea that the filaments form because there are AGN-driven outflows, and the warm components will cool rapidly and form filaments eventually. So the third question I wanted to talk about is the preservation of dust inside these systems. For example, in the Centaurus cluster, NGC 4696, you can see multiple dust lanes that are co-spatial with the H-alpha filaments. So these are very interesting phenomena that cannot be explained by precipitation models, because if you form filaments from the hot intra-cluster medium, then it's usually unlikely that the dust will survive due to thermal sputtering of the dust grains. And also in Perseus A, we also have detectable pH feature at around 10 kiloparsecs from the AGN, which means somehow the dust can survive in the filaments, however they form. So we looked at. Okay, yeah. This is actually the second last slide, so I should be fine. So we looked at the dust sputtering inside our fiducial model of launching outflows from the center of the cluster, and here is a plot for the minimum dust size as a function of initial temperature of the outflows. We can see for dust size less than 1 micron, if your outflow temperature is less than 4 times 10 to the 6 Kelvin, there's a chance for the dust to survive in the outflows before it cools, right? Because these cooling are also rapidly happening. And if you compare the dust sputtering rate on the right, you'll see that, the blue color here represents sputtering rate less than 10 to the minus 7 micron per year. So that means, for dust size around 1 micron, it takes 10 million years for the dust to be sputtered, but the gas will usually cool. The warm outflows will usually cool before that happens. Okay, so moving on to the last slide. So this is my summary. Basically, I've asked 3 questions in the beginning of the talk, and we've answered all of them. First, the ram pressure promotes AGN-driven outflows whose cooling time is shorter than the rising time. So the outflows eventually form cold filaments with low line of sight velocity. And under this framework, the intra-cluster medium properties, particularly T cool over T free fall, agree pretty well with the observations, and the extra cavities can co-rise with the filaments. And the third and last one is moderate offload temperature allows for dust to be preserved in the filaments. So that helps explain why sometimes you can see co-spatial dust lanes with the H-alpha filaments. I haven't had time to finish every aspect of the paper, so if you're interested, you're more than welcome to look more into our publication. Thank you. I'll take questions now.
Thank you very much, Hugh, for this very, very interesting talk. Do we have questions? Let me see in the Q&A. Paul Sell has a question here for you. What is the injection opening angle of these AGN-driven outflows, and is there precession? And a follow-up question is, does this change with power and velocity, as seen, for example, in FR1 and F2 jets?
Let me start with the first question. So, so in terms of the modeling of jets in our simulation, it's directly in the vertical direction. So there's no precession, and there's precisely no opening angle because it's only launched in the positive and negative z direction. But because there are dense cold gas around the central AGN, so sometimes the outflows can be deflected just because there's something blocking their way. So that's why sometimes you can see that the outflows will actually go sideways and not following the jet direction. So sorry, I forgot the second question.
So the second part was, does this change with power and velocity, as seen, for example, in FR1 and F2 jets?
Right. So that is something sort of handled by the simulation itself, right? So it's sort of a combination of shock heating from just turning kinetic energy into thermal energy of the gas. But I'm not sure what precisely do you want to know?
Let's see. Well, maybe Paul, if you want to clarify, and otherwise maybe too, if you can. Well, we cannot really say, you can talk about it over coffee in a break, but maybe in an email exchange, clarify. Let me just ask one more question before we go to the next talk. Actually, first
Sure.
a comment from William Burgett. No question, just want to appreciate the very nice talk. And Irina Zurafleva also says, nice talk. And then as a question, did you study dynamical coupling between the different gas phases?
Sorry, dynamical what?
A dynamical coupling between the different gas phases.
Not precisely. So this is sort of just a very simple treatment of different components. We kind of treat them as if they're cooling on their own while flowing out from the center of the cluster. And it kind of goes very well with what we see in our simulations. So we haven't thought about the coupling between different components, but it's definitely possible because they'll interact with each other and do things.
Okay, great. Well, thank you very much again for this very nice presentation.